In our world, we talk about luck, about chance, but does something like true randomness even exist? When you flip a coin, it feels like everything depends on chance, heads or tails. And yet, if you knew the exact force of your throw, the angle, air resistance, the fall time, you could predict the outcome. If that's the case, and World of Warcraft is, after all, just a set of instructions, hundreds of thousands of lines of code executed by a computer, then does luck really exist in this game? When you go to Farm Invincible or Alar for the 100th time, you might start to wonder, can this be predicted? What does it actually depend on? Before we answer those questions, there's one thing worth pointing out. Blizzard never reveals its source code, so the exact randomization system in World of Warcraft remains a mystery. But there are emulators, fan-made copies of the game used to run private servers. In their code, we can actually see how the entire RNG process works. What's more, this solution is well known and widely used across the game industry. We can safely assume that Blizzard uses an identical or at least very similar system. That solution is SFMT, the SIMD-oriented Fast Mersenne Twister. It's a pseudo-random number generator, which means the numbers it produces appear random even though they're actually generated by a mathematical formula. But before the generator can even start, it needs an initial point, a seed. A seed is simply a sequence of numbers that SFMT uses as a starting point to generate its random values. In theory, you could use any number, for example, the boss identifier. But if we want true randomness, we have to go deeper, to the operating system itself. There, in the server's kernel, there's a special file, dev/random. This file stores a stream of bytes that the system constantly generates, based on surrounding chaos. How? By monitoring physical and software events from various sources, the network, disk activity, CPU operations, even devices like a mouse. And here we already have a partial answer to the first question, because some of these events aren't just simple coin tosses. That includes things like thermal vibrations and transistors, electronic noise and tunnel diodes, and phenomena happening at the quantum level. The kind that, according to modern physics, are truly unpredictable. But there are also more relatable sources, like how often you click your mouse. Because whether the source is quantum or classical, for the system what matters most is when and how often something happens. Let's say you've just clicked your mouse. That signal goes to the processor, which records its timestamp with nanosecond precision. Then the system compares. How much time has passed since the previous click? That result is further mixed with other data, the event source identifier, the current state of the processor, and so on. From this combination, the system tries to answer one question. How unpredictable was that event? And that very unpredictability, that amount of chaos within an event, is what we call entropy. Let's go back to our coin toss. Two possible outcomes, heads or tails. That's exactly one bit of entropy. If a dice roll can produce 6 outcomes, then according to the formula, we get a little more than 2.5 bits of unpredictability. But our mouse click is something far more complex. The system analyzed the time difference between clicks, the rate of change, and even the acceleration of those changes. Let's add a few events, and go over the key columns. Don't worry, it's actually quite simple. The time difference is the timestamp of the new event minus the previous one. The rate of change is the time difference of the new event minus the time difference of the previous event. And the acceleration of change is the rate of change of the new event minus the rate of change of the previous event. Now let's focus on click number 5. Our formula looks similar to the one we use with the dice. Let's simplify it, step by step. This value is our rate of change, and this one is the acceleration of change. First, we take the absolute value, which means removing the minus signs, if there are any. Then we compare the two values and pick the larger one. That value goes into the formula. After calculating, we get roughly 18.19. That means the entropy of this event is about 18 bits. But to avoid overestimating its own randomness, the system limits the maximum contribution of a single event to 11 bits. Those 11 bits are our ingredient, a small portion of chaos added to the great soup of randomness. Let's say our soup already had 180 bits from previous events. We add our 11 bits, and now we have 191. But for the system to consider the soup ready, it needs at least 256 bits of entropy. That's 2 to the power of 256 possible states, a number comparable to the number of atoms in the entire solar system. Once that level is reached, the data is passed through a CSP RNG, a cryptographically secure pseudo-random number generator. It's the one that stirs our entropy soup, adding even more randomness to the collected data. We'll skip the details of how CSPRNGs work internally. The key thing to remember is this. The output of the CSPRNG is a stream of bytes. Our desired seed, now fully seasoned with entropy from the system. Here's an example of a seed. This long string of numbers and letters is what the pseudo-random number generator uses as its starting point. From it, the game decides the outcome, whether the boss drops your mount or you'll have to try again. The SFMT randomization system doesn't need that entire long string of bytes. It only needs 32 bits. The first 4 bytes of our seed, in decimal form, that gives us this number, and that's where it all begins. From this single value, SFMT generates a table made up of 624 elements, each one being a 32-bit integer. The first element, S0, is our seed. The following elements, S1, S2, all the way up to SO623, are generated according to a specific formula. Let's take the first step. We start with S0 and use it to create S1 in the following way. The generator takes the previous number, S0, and shifts its bits to the right by exactly 30 positions. Next, it performs an XOR operation, comparing each bit of S0 with the corresponding bit of its shifted version. If the 2 bits are the same, the result is 0. If they're different, the result is 1. This way, a new transform number is created. Next, our result is multiplied by a constant value, which in SFMT equals this. The multiplied number becomes too large, so the system trims it down to 32 bits. After truncation, we get this value. Finally, we add the index of the element in the table. In this case, we're generating S1, so we add 1. We then check if the result still fits within 32 bits, and it does. And that's how we obtain our completed S1 element. In the same way, we generate the next numbers, S2, S3, all the way up to S623, always combining them with the previous value and filling the entire table. But this is not the end. Once the table is filled, we reach the step that gave the generator its name, the twist. It's from this twisting of bits that the name Mersenne Twister comes. The twist step shuffles the entire table and produces a new table of values. Each element is processed using the same pattern. As a result, each new element is a mixture of several previous values from the table, stretched, shifted, and bit twisted in different ways. And now we get to the most interesting moment, our chance for a drop. Let's assume this is a fresh server and we're making the very first loot roll. In that case, the value S0 will be used. For the next roll, the game will take S1, then S2, and so on, all the way to the last value in the table. What happens when the table runs out? The algorithm performs another twist, and from the previous table it generates a new one, containing another 624 fresh numbers ready for random rolls. In practice, this means 2 to the power of 19,937 minus 1 possible combinations, a number so huge it's greater than the number of atoms in the entire observable universe. And all it takes is changing just one element, the seed, and this entire random universe starts over from scratch. So let's assume we just killed a boss and the server needs to roll whether we get a mount with a 1% drop chance. We got the number from the table S67. This is a number in the range from 0 to 4,294,967,295. That is, from 0 to 2 to the power of 32 minus 1. To convert it into a percentage value, the game simply divides it by the full range. Now the server compares this result with the drop chance threshold, 1%, which is 0.01 in decimal form. Since 0.01676 is greater than 0.01, the mount doesn't drop. In other words, the server rolled 1.67%, but we needed less than 1%. Close, but not this time. Maybe next week quantum fluctuations will finally decide you've suffered enough, and they'll give you that mount at last.